All right, so binary and representing data in various ways. We'll talk about how this works. This is one of the major flaws in C and other languages, is that you have trouble converting numbers, overflows and underflows and so on. So I think we've talked about these binary games. Let me just take a look back and see which ones you've done in this course, because I get them all kind of run together in my head. Maybe I haven't demonstrated in this course yet, but maybe we have. Oh, you did nibbles last time. Okay, so we've done some of them, but we'll do some more later. So we've begun to do binary games, which is the best way, I think, to learn them one lesson at a time. All right, so then there's signed integers. Now, this is something that takes a little getting used to. Positive numbers are just represented as you'd expect. 0, 1 is a 1, 1, 1 is a 3, and so on. But negative numbers, the leftmost bit is treated as the clue that it's negative, and all the other bits are treated as 1 or 0. So what you have is you take minus 2 to the n minus 1 plus these other digits. So this is weird, and it looks like this. If you're going in positive numbers, you have 0, 0, 0, 1, 0, 1, 0 is 2, 1, 1 is 3. This is what we're used to. But for negative numbers, minus 1 is 1, 1, 1, 1, which would be 15 normally. But you treat that as minus 1, minus 2, minus 3, and minus 4. It is pretty screwy. It's a strange system, but that's what we're all using. This is how you have negative numbers in a nibble, and the same thing for all integers. So to find the negative, you flip all the bits and add 1. So if I have 13, 13 is 1101, so you flip all the bits. All the zeros go to 1s, these go to 0, and then you add 1. So you get here. So it is kind of screwy, but that's how you create the negative, the ones complement negative numbers, which is what we're all using to represent negative integers. All right, so in C, int is a signed integer, and unsigned int is unsigned. So by default, int includes those positive and negative numbers. All right, and then you got binary arithmetic. So if you add them, you want to add 2 plus, this looks like 11. You get 13. And so if you add them, you'll add the 0 and 1 and get 1. You'll add the 1 and 1, you'll get a 0 and carry the 1, which then you add a 0, so 1 goes here and 1 goes there. So this is now 8 plus 4 is 12 plus 1 is 13. So 2 plus 11 is 13, and you can do the addition the same formal way in binary that you do in base 10, by just adding the columns from the right to the left and carrying ones that roll over. And you can do subtraction. So if you have 1, 1, 1 minus 1, 1, that is 7 minus 3. And so you can just subtract them. Right, one way to do it is convert to addition. I would just do it by subtraction. 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1. So you'll get 1, 0, 0. But what they did here was turn the negative number into a 2's complement number, so that you flip every bit and add 1. Remember, that's it. So you change 0, 0, 1, 1 to 1, 1, 0, 0, and then you add 1. And now you'll have 1 and 1 is 0 and carry the 1. 1 and 1 is 0 and carry the 1. And in the third one, you'll have 1 and 1 is 0, you have the 1, and that one will carry here, and you'll have 1 that rolls over, which escapes your 4-bit limit. So you do end up with the right answer, 1, 0, 0, or 4. It's just a little confusing and hard to see, but this is what computers really do, is turn the negative number into a 2's complement number and then add them. All right, and there's subtraction again. I think we've already talked about that. And here's addition, which looks like unsigned integers, I'm guessing. So 10, 11, and 1 here. This one will roll over, so you'll get 1, 1, 0, 1. So, all right. Anyway, let's try a Kahoot about that stuff. I see 6 people online. There may be enough to make a Kahoot competition here. Let's see. This is chapter 4. And there we are, chapter 4a. All right. Let's see if we get any takers here. All right, so what is that number in decimal? 0b is Python's way of representing binary. So 1100. Yep, all your answers are correct. It's 12 because this is the number of ones, number of twos, fours, and eights. So that's 4 plus 8, that's 12. Good? Oh, and we got 4 players. Good. Okay. All right, how about this one? 0e in decimal, that's a hexadecimal. F is 15 and E is 14. I don't think I've talked about that in this class yet, so you may not know that one yet, but the right answer is 14, and we'll talk about that later. All right, that's part of why these things are extra credit. Sometimes they're not completely fair. And all right, what's the largest value you can store in a signed byte integer using 2's complement? 127. If you had a whole byte, you could go up to 255 with an unsigned integer, but with a signed integer, the left bit must be 0 for positive numbers, so the biggest number has 7 ones to the right of that, and that's 127. All right. Let's go on here. So now we can talk about overflow, which is probably the most interesting part of this. So if you keep adding 1, reach a certain point here, and if you keep, now if it's an unsigned integer, you can keep adding 8, 9, 10, 11, 12, but when you have 15 and you add 1 more, it rolls over to 0 because you only have 4 bits. There is a bit that rolls off to the left. If you had more bits available, like you had a whole byte, then you'd have 16, but you can't have 16, so it rolls over. And these overflows are a problem. When you're adding to a number and suddenly it gets smaller instead of bigger, that can lead to security flaws. And a signed overflow is down here. If you add positive numbers above 7, they turn negative on you. If you have negative numbers and they go below -8, they turn positive on you, so it leads to the same kind of problem. All right. And then there's bitwise operators. So we talked about this before. An AND means both numbers have to be 1 in order for the result to be 1. So you compare the bits. If the bit in the first value is 1 and the corresponding bit in the other value is 1, you have a 1. Otherwise, you get 0. That's an AND. The bitwise OR is the opposite. If either one of them is 1, the answer is 1. Only if they're both 0 do you get 0. Now, I should mention this is important as we move in. If you consider cryptography, both of these show that the AND and OR destroy information. If I feed in a bit stream that's half ones and half zeros, and I combine 2 bit streams with this technique, 3/4 of the bits will turn to 1 if I'm using OR, and 3/4 of the bits will turn to 0 if I'm using AND, and in both cases that destroys information. So you cannot use these processes for cryptography because they irreversibly destroy information and there would be no way to decrypt the message. That's why you don't use these in cryptography. You use exclusive OR, which is here, because now 0 and 0 gives you 0, but if they're both 1, you also get 0. You only get 1 if it's 0, 1, and 1, 0. So now if I feed in a bit stream that's half ones and half zeros and XOR it with another bit stream that's half ones and half zeros, the outcome will still be half ones and half zeros. I don't destroy any information, and this can be reversed. In fact, XORing this against either one of these will give you the other one back. So if this is the plain text and this is the key, then XORing the ciphertext with the key will give you the plain text again. Because another way to look at it is where you have a 0 here, you don't change the bit. Where you have a 1 here, you flip the bit. So I have the 0 here, I don't flip that bit. And so to come back, I don't flip it again. This one, I flip it. And to get back to the original, I flip it again, getting back to there. So, all right. Then there's bitwise not. This is just not an A. This reverses all the bits. All the zeros go to ones, all the ones go to 0. And then there's bit shifting, where you just shift it to the left. So here, 13 is 1101 here, and if you shift it left 3, you just move it left 3, put 3 zeros on the right, and move the 1101 over here. That's the same thing as multiplying it by 8. Every time you shift it left by 1, you double it, because whatever was in the 1's place is now in the 2's place, and whatever's in the 2's place is now in the 4's place, and so on. So this is multiplying by a power of 2, left shifting. Although, you have to consider an issue. What happens when you have bits that fall off the left edge? What do you do with them? All right, so a logical right switch will prepend 0. So if you logically shift this to the right, then this one, we're going to shift it to the right. It looks like 3, I think, or 2. Yep, wait, 0, prepend 0, 1, 0, 1, yeah, 1, 0, 1, 1. Okay, I've shifted it to the right twice here. These ones have both fallen off. I have the 1100 and I have the 10, and I put 2 zeros there. Okay, so this is shifting it to the right twice. Now, an arithmetic right shift prepends a copy of the most significant bit. So the fact is this thing was negative, so I'm going to keep on preserving it negative, so I'll keep copying this bit. Those are the difference between a logical right shift and an arithmetic right shift. All right. So in C, it does a logical right shift for unsigned integers and an arithmetic right shift for signed integers. That's how it works. It's an interesting fact. I don't think it's really going to matter when we get to assembler. We're not going to do these arcane things, but that's how it works. All right. All right. And I've got some more binary games. You can play with those things. We'll get to them eventually. All right. So then we got the integer byte order. This is endianness. And this we will have to confront a lot when we get to binary exploits. So if you have a 16-bit integer, the higher order byte is A and the lower order byte is B. So this is two possible layouts. You can put the most significant byte at the lower memory address and the least significant at the higher address, or you can put them in opposite order. All right. x86 uses little endian. Oh, all right. Let me turn on the projector. All right. So little endian, if you initialize a 4-byte integer with A being the most significant, B, C, D, then it will store it with the least significant byte at the end. All right. Well, let's see, to A, B, A, D. Right, the least significant byte is D. That's at the start. That's what I want to see. So this, by the way, I'll point out this is very strange. A logical sequence would be this way. The most significant byte here. So as you read them, you'd find the most significant bit here, 8 bits decreasing in significance, and then another 8 bits decreasing in significance here. That would be a logical way to write down a 16-bit integer. But this is what x86 processors really use, and it is very strange. The most significant bit is here, and then the bits are less significant as you proceed upward in address here within the byte, and then the next bit is over here. So it's strange and broken. The byte's significance is not monotonic. But that's what we're really using. So here you have a number that's AA, BB, CC, DD. So A is the most significant and D is the least significant, and yet you put the least significant first and the others. So it's screwy. All right, and that's what you see here. This is big endian, which would make more mathematical sense, but it's not what the processors we're using use. They use little endian. All right, and then real numbers in binary. I always kind of wondered how this worked for years. You have fixed point representation. You're going to have numbers to the decimal point and fractions. And so the value of each digit is an 8-bit number with 2 bits after the fixed binary point. This is one way to do it. And floating point is typically what you have. So you have a sign bit, then you have exponent bits, and then you have the bits for the significant value. So this is what you typically have, and that's why you write these as like 2e7, 2 times 10 to the 7. That's the only way to handle real floating point that would go for a large range of values. And therefore, it should be obvious that all floating point numbers are approximate. You only have a certain number of bits to record the significant multiplier. And so if you had a number like pi, you're never going to be able to represent it exactly. You're only going to get a certain number of bits before you've run off. And so if you have money and you keep adding and subtracting to the balance in an account, it won't be accurate after a while. Which is why you really should use integers for money. All right, let's try 4b, which is here. And then we'll do some of those binary games, which certainly go with today's lecture. There were 4 last time. I'll wait a bit to see if more are coming. All right, so what do you get when you AND those two numbers? You'll get 0, because the first 3 bits here are all 1, and these are 0, and you only get a 1 if they're both 1. The last one here is 0, and the last one there is 1, so all the bits turn to 0 if you combine them with an AND. All right? Because an AND means both corresponding bits have to be 1 for you to get a 1, otherwise you get a 0. All right? How about if you do an XOR between these two numbers? All ones, because these 3 ones combine with those 3 zeros, and a 1 and a 0 are a 1 in exclusive OR, and this 0 goes with a 1, so they all turn into 1s, and you get this number, all right, which is 15. Good? All right, and what happens if you shift right that number twice using arithmetic right shifts? Oh, this is the right answer. I made a mistake in the right answer. The wrong one is marked right here. Now, that's really not fair, but a good thing there's so few players today. But with arithmetic right shifting means you fill a pad it with 1s, not 0s. This is the right answer. Let me make a note. That one is wrong. That is 4B, last Kahoot, wrong answer. Very rude. Sorry about that. 4B, last Kahoot. All right. I can't change it now, but that's rude. Anyway, all right. That's a logical right shift answer. I write these and I make mistakes sometimes. I could use AI to write them, and then the AI would probably make more mistakes. Anyway, all right. So that's the lecture. And now I just want to do demonstrations. Let's see what I planned today with C101, which I think is binary games. Yep, it is. All right. We already did nibbles last time, so let's do a couple more of these. All right. Bytes and perhaps hex. Let me start recording.